Let's do a quick problem practicing finding the net electric field at some point due to a couple of point charges. We've done things like this in class before, but maybe it's good to have some practice. In particular, in this case, I have a positive 5 nanocoulomb point charge over here and a negative 3 nanocoulomb point charge on this side. And I want to know, for some reason, the net electric field at this position up here, a particular place, 5.6 centimeters up from the two charges, and it's 10.5 centimeters over from there, 19.2 over from there. I've got this particular set of dimensions. I want to know the net electric field at that point. Well, okay, before I start doing computations and things, let's just do a conceptual rundown, make sure we know what's going to happen first. Positive charges, we know electric fields point away from positive charges. So that positive charge is going to make a contribution up at this point that's aiming somewhere kind of like this. I'll call that maybe E plus is going to be pointing up away from that positive charge. Meanwhile, the negative charge over here is going to have a contribution pointing straight down toward it. So some sort of arrow like this that I could call E minus, of electric field vector going that way. And the net electric field at that point is going to be the sum of these two vectors. It's the usual sort of vector sum. We'll talk about it when we get there, but we've done vectors for a long time now. Same deal happens here. So what I want to do is figure out how we can actually compute this mathematically, how we can work this out. And the strategy is going to be based on Coulomb's law for electric fields. We all know Coulomb's law. The statement is the magnitude of the field is equal to Coulomb's constant K times the absolute value of the charge giving the field divided by the distance squared from the charge to the point where you're measuring the field. And as we know, away from positive toward negative charges is the direction. We have to get a vector, magnitude and direction, that's our deal. So here's the strategy we're going to use for each of the two charges out here. We're going to start by finding the distance from this charge to our measurement point, or from this charge to our measurement point. We'll do that. Then we'll use Coulomb's law to find the magnitude of the field at that point. After we've done that, we'll then go on and find the angle. We've got to find an angle to be able to do mathematical things, and then find the components, the x and y components of the field there. I'm using the standard x and y, x horizontal, y vertical, to the right and upward. I'm using the standard components for this problem. All right, so let's look at the story. We'll start with the negative charge over on this side. For the negative charge, I want to start by finding my distance. The distance, I guess, is what I'd find going straight along here. I might call that r minus because it's the radius, or the distance r from the negative charge to here, from the minus, so r minus. And this is just a right triangle. I know that r minus, by the Pythagorean theorem, is the square root of 10.5 centimeters squared plus 5.6 centimeters squared. And pulling out a trusty calculator, I get that 10.5 squared plus 5.6 squared gives me square root. I get 11.9 centimeters is my distance over there. 11.9 centimeters between those two. Now that I know r, I can plug this into my electric field strength equation. I can say that the electric field, due to the negative charge, the magnitude of that field, is Coulomb's constant. We're just going to approximate it as 9.0 times 10 to the 9th Newton meter squared per Coulomb squared. 8.99 is a bit more accurate, but that's what, like 0.1% off, so we're pretty close. This Newton meter squared per Coulomb squared times absolute value of the charge. 3 nanocoulombs is 3.0 times 10 to the minus 9th coulombs is my absolute value. That's a 3, it just doesn't look like one. Okay, and then we're going to divide by the distance squared. My distance is 11.9 centimeters. I want to be in standard SI units, so I'll divide by 0.119 meters squared. I want to do all those calculations. So I have my 9 times 10 to the 9th times 3 times 10 to the minus 9th. Hey, those cancel out nicely enough. Divided by 0.119 squared. I get that my E minus is 1906.6. I could keep going forever. 6.4. And units, meters squared cancels out. One of the coulombs cancels. Newtons per coulomb. Those are the units of electric field, so I feel good about this. I have a magnitude of an electric field. Great. Okay, so I have my magnitude of the field. Next step in my strategy, I have to figure out what the angle is that it's acting at. In my picture, I've drawn my E minus vector pointing toward the negative charge, and so I can see it lines up exactly with this right triangle. Why don't I go ahead and just label an angle of the right triangle, theta minus here, to be the angle. That angle will be the same angle that that arrow is pointing at, that E minus vector is pointing at. So I can figure out that theta minus using standard trig stuff, just using the picture. This is always how it's going to work. You've got a picture showing where you're measuring. That same shape will tell you which direction your arrow is pointing, which direction your vector is pointing. So here, I know that tangent of theta minus is equal to the opposite side, 5.6 centimeters, divided by the adjacent side, 10.5 centimeters. So let's see, 5.6 divided by 10.5, inverse tangent. I get 28.07 degrees. That's my, yes, tangent equals this. So that's my theta. My theta minus is this. When I do an inverse tangent of that ratio, I get 28.07 degrees. Getting a little ahead of myself. So okay, I've got an angle there. Next, I want to find my components, the x and y components of E minus. And I can do that pretty easily. I know that E minus x and E minus y, well, the x component, let's look at it. I always start by looking at plus and minus. The E minus is pointing in the negative x direction more than positive, and negative y more than positive. So both of these are going to be negative numbers. Then I know it's just the magnitude minus the magnitude E minus in each case, times, we've got to do some trig stuff, right? The x component, E minus x, is going to be, I guess maybe I should draw this a little larger so we can see what's going on. If I just copy it down here, I will have, here's my E minus vector. Copy it down. Here's my theta minus. And here's E minus y and E minus x. I know that theta minus is my 28.07 degrees. So that means x is adjacent to it. So I do cosine of theta minus. Y is opposite my angle. So I do sine of theta minus. And the numbers I get, when I do that, let's see, the sine of this angle, let's see, cosine, I get 0.8823 times my 1906.64 equals, I get negative 1654.2 newtons per coulomb for that one. And down here, I get, same thing, 28.07 degrees. Sine of that is 0.47 times 1906.64 equals, down here I'll get minus 897.2 newtons per coulomb. So here I've broken my E minus into components, an x component and a y component, and that is something I'm going to keep for finding my total. I've done all this stuff for E minus. Now I just need to repeat this for E plus. So you know what, I'm going to sort of reserve this thing. Those are results that I want to hang on to for later. But now I want to go through and follow the exact same procedure for the E plus, for the plus one up here. We're going to do the exact same story. We go through the exact same story, just looking at the positive charge's effects instead of the negative charge. Let's try it out. Okay, so same thing. We start out by finding the distance. Where's my distance? Well, it looks like here is my r plus. There's my distance from the positive charge. Let's work it out. R plus is equal to the square root of 5.6 centimeters squared plus 19.2 centimeters squared. When I do that, I've got 5.6 squared plus 19.2 squared. Ooh, I get exactly 20 centimeters. 20 centimeters comes out, so that's my distance r plus. Next, I do my magnitude. The magnitude of this electric field due to the positive charge, same thing, Coulomb's law. We do 9.0 times 10 to the 9th Newton meter squared per Coulomb squared times absolute value of the charge is 5.00 times 10 to the minus 9th coulombs divided by my distance, looks like exactly 0.2 meters, so 0.200 meters squared. When I multiply all that out, I could almost do this one in my head. Let's see, that's 45 divided by 0.2 squared. I get 1125 newtons per coulomb. And so that's our magnitude of this. Again, this is the exact same procedure we did before. Find the distance, then find the strength of the field. Next up, we need to figure out the direction of the components. Again, this isn't bad. If I just call this angle theta plus, give it a name, theta plus is the angle of the up from the positive charge toward here, then this vector up here, my E plus, is going to have the same theta plus angle at labeling it as well. You just copy it down from the figure. You copy it down from the positions to get the direction of your field. So because this E plus arrow has to go exactly along that same hypotenuse, same deal. So I can figure this out. Let's see, clear myself a little space. Clear a bit more, okay. So I can do the same thing. I know that the tangent of theta plus is going to be 5.6 centimeters over 19.2 centimeters. And that'll tell me theta plus is, I just do an inverse tangent of this thing. Let's test it out. 5.6 divided by 19.2, inverse tangent. I get 16.26 degrees. Okay, 16.26 degrees. Now I just go through into the components again. I've got E plus X component and E plus Y component. Again, I'm going to look at the two pieces. I'm going to look at this first to get plus and minus signs right. It looks like it's going to the left, so it's a negative X in my coordinates. It's going upward, so it's a positive Y in my coordinates. And now I just do my same thing. I do my magnitude, negative E plus times, let's see, X is adjacent to the angle I have labeled, so that's going to be cosine of theta plus, and that is, if I multiply that out, I get negative, let's see, 1125 there times my cosine of theta plus, cosine of 16.26, 16.26 cosine, I get negative 1080 newtons per coulomb. This one, I do the same thing, the magnitude E plus times the sine of theta plus. Again, I'm just doing the right triangle business. Doing this one, I end up getting, let's see, 1125 times the sine of 16.26. And I get positive 315 newtons per coulomb. So at this point, I have X and Y components for the negative charge and for the positive charge's contribution to the total electric field over here. Now, having done all that, I'm supposed to put it together. Now that I've done all that, the net electric field is just a vector sum. You just sum up the components. There's nothing new and complicated about it. I sum up the components. I find that E net X is equal to, just add them up, negative 1080 newtons per coulomb here, minus 1654.2 newtons per coulomb, equals, I can do that, 1654.2 minus I get minus 2734.2 newtons per Coulomb. That's my net X field. And E net Y, my Y component, going to be the same deal. Here I've got plus 315 newtons per Coulomb from the plus charge, and the minus gives me minus 897.2 newtons per Coulomb. Adding those up, let's see, 315 minus 7.2, I get minus 582.2 newtons per Coulomb. All right, so that's my net field, and on some level I'm done right now. I've specified the X and the Y components of my net field. It works out pretty well. We can ask, does this make sense? Is this a sensible thing? And, well, what am I? This looks like it's 4 or 5 times more X than Y. Well, that makes some sense looking at these two vectors. If I were to draw a vector sum of the E plus and the E minus that I have drawn up there, they're going to partly cancel out in the Y direction, and they're going to reinforce each other in the X direction. So I expect a bigger X than a Y. And so that makes sense. If I just drew my vector sum of those two, let's think about it a little bit. The plus charge is much farther away than the minus charge is, and it's only a little bit bigger. So I expect this positive, the E plus arrow, to be a bit shorter than the E minus arrow, somewhat shorter. So if I added these two together, just doing a visual vector sum to begin with, oh, that's steeper than my actual picture. Let me get this at least a little bit right. There's my E plus, and if I added to that my E minus, which is a little longer and a little steeper, E minus, if I add those two together, you add vectors head to tail, remember, my net electric field then would look something like this. My net electric field should be way to the left and a little bit down. That's what I've got here. So that makes me feel pretty good about my results. And really, we could stop right here. This is already specified the complete electric field. If we wanted to, we can go on and calculate the magnitude and the angle of this field. Magnitude's easy, and vector components. This is just vectors at this point. Magnitude is easy just Pythagorean theorem stuff. The magnitude of the net field is just the square root of minus 2734.2 newtons per Coulomb squared plus minus 582.2 newtons per Coulomb squared. And if I do that, what do we have? 2734.2 squared plus 582.2 squared. I get 2795 newtons per Coulomb as my overall strength. 2795. I don't know where I may have had what my significant digits are here really. I'd probably even call this just something like 2800 newtons per Coulomb. If I rounded to 3 significant digits, that would come out to be 2800. That seems pretty close to the level of significance I'd want. 2.80 times 10 to the third, if you want to be really precise. So I've got that. That's my net field. And then I can ask, well, what is the angle of this going to be? The angle I'm talking about, I guess, would be maybe down from horizontal. If I look at this angle in my picture, and there I can do the same thing. I know that tangent of theta in that picture is y component over x component, opposite over adjacent. So absolute value of EY over EX. And in our case, we've got those numbers. I can just work this out. Y, that's plus absolute value 582.2 newtons per Coulomb divided by, and I'm canceling out the plus and minus, I'm absolute valuing 2734.2 newtons per Coulomb. If I then do an inverse tangent, I'll get 582.2 divided by 2734.2. Inverse tangent, I get 12.0 degrees. I get 12.0 degrees, and that gives me my results. That gives me my my angle down from horizontal, as shown. in the picture, and it tells me magnitude and direction. So I can either specify my final answer in terms of the net x and y, or I can specify it in terms of the magnitude and the angle. Either way, we've done the complete calculation. Just to recap, the key ideas were we went one charge at a time. We looked at each charge. We started by calculating the distance from the charge to the place we're measuring. We then calculated the magnitude of the electric field using Coulomb's law. And then we started worrying about vector stuff. We worked out the components of the vector that based on the angle. We worked on the x and the y components of that vector. Then we repeat the whole thing for each charge. If I had 18 charges here, we would just do this whole same thing 18 times. Repeat the whole thing for each charge. Once we have the list of all the x components, we add them up. Once we have a list of all the y components, we add them up. We get our net components, and then we just do standard vector stuff if we want magnitude and direction. That's the whole story, and I hope that's a decent little review of how you do electric field problems.